All right, get ready. We're taking a deep dive into the world of coordinate geometry today.
Sounds fun.
It's a fascinating area. It's where shapes and equations kind of meet.
Yeah.
And trust me, it's a lot cooler than it might sound at first.
It is, yeah. The stuff you've given me, all these notes and illustrations, it's like really rich, really. A lot to dig into here.
Yeah. It's like we're piecing together a treasure map.
I like that.
Each concept is like leading us to a better understanding of how these shapes work. So first things first, what exactly is coordinate geometry?
So it's this really cool idea that we can actually describe any point in space using numbers. We give them coordinates.
Right.
And then from there, we can use equations to actually represent lines and curves and even like complicated shapes. So it's kind of like translating the visual world into the language of algebra.
I love that. That's a great way to put it. So I vaguely remember this from like high school, something about X's and Y's.
Right.
But why bother with all these equations when we can just, see the shapes?
Right. Well, think about it. Our eyes can be deceiving, right? I mean,
Yeah.
things might look parallel or things might look equal, but are they really?
Right.
Coordinate geometry gives us this precise way to measure and analyze and really prove these relationships.
Got it. So it's like having this like super powered ruler and protractor like combined.
I like it.
So our sources mention two main coordinate systems, Cartesian and polar.
Right.
Are those like different dialects of this geometric language?
Yeah, that's another good way to put it.
Okay.
They're just different ways of defining those numerical addresses for the points in space.
Gotcha.
So Cartesian coordinates, those are the ones you're probably more familiar
Okay.
with the X and Y axes.
Yes.
Those are perfect for describing things that are, laid out in grids, like streets in a city.
Yeah, like a chessboard.
Exactly, like a chessboard, exactly.
Okay, so that's Cartesian. And then what about polar coordinates?
Right.
Those sound a little bit more, mysterious.
They do sound a bit more mysterious. Think of a radar screen.
Okay.
So instead of using horizontal and vertical distances like you do with Cartesian,
Yeah.
you're using an angle and a distance from a central point.
Got it.
So that's really the essence of polar coordinates. And those are perfect for describing things like circular motion or anything that kind of radiates outwards.
Okay, so those are our coordinate systems. That's our map, so to speak.
Oh.
But how do we actually navigate this landscape? I see something here about a distance formula.
Right. The distance formula is like our compass, right?
Okay.
It tells us exactly how far apart any 2 points are, no matter where they are on that map.
And that seems, pretty straightforward, right? Just measure the distance between 2 points. What's so special about that?
Well, it's more than just measuring. It's about using the coordinates and a bit of algebra to calculate the distance precisely. And with that seemingly simple formula, we can actually unlock so much. Like, for instance, we can tell if 3 points are collinear.
Okay.
That means that they lie on the same straight line.
Oh, okay. So if the distance between the 3 points, they add up perfectly.
Right.
They must be on a line.
Exactly.
Okay, but what if they don't add up perfectly? Does that mean we made a mistake?
Not necessarily. It just might mean that they form a triangle.
Okay.
And even if they don't seem to form a triangle, like visually, the distance formula can actually help us reveal those hidden relationships. Take illustration 1, for example.
Okay.
It tries to find points on the x-axis a certain distance from a given point.
Okay, and what's the catch?
Well, when we apply the distance formula,
Yeah.
it turns out that there are actually no such points. So it's this fascinating case where algebra actually proves something is impossible that might not be immediately obvious just by looking at the geometry.
Wow. That's really cool. So it helps us confirm what we see and kind of uncover these hidden truths.
Exactly.
That's super cool.
Yeah.
So I'm starting to see why this coordinate geometry thing is so powerful.
Yeah.
And we're just scratching the surface here. So let's move on to another key tool here. I see something about a section formula.
Right.
Okay, what does this one do? Section me piece of knowledge, please.
Okay, so think of a line segment, right?
Okay.
The section formula lets us find the coordinates of a point that divides that segment in a very specific ratio,
Right.
like 1/3 or 2/5.
Got it. So it's not just finding the midpoint. It could be any point that splits the segment proportionally.
Exactly.
Uh-huh.
It's like having this precise cutting tool for lines.
And this must have some applications beyond just like theoretical geometry.
Yeah. Oh, absolutely. Absolutely. Imagine, for instance, you're an architect and you're designing a bridge and you need to figure out exactly where to place the supports for optimal weight distribution. The section formula can actually help you pinpoint those exact locations.
So coordinate geometry, like the secret language of architects.
Kind of, yes.
I love it. And I see we have an illustration that kind of dives into this, illustration 3. What's the scenario here?
Yeah, so this one shows us how we can actually use the section formula even when we don't actually know the ratio of the divided segments. So by knowing the coordinates of the endpoints and the dividing line, we can kind of work backwards and figure out that ratio.
Oh, that's neat. It's like a detective game.
It is. It is.
I love it. Okay, so we've explored how to locate points, measure distances, and even divide segments, like with pinpoint accuracy. So what other treasures are kind of hidden in this coordinate system? I see something about special points in a triangle.
Ah, yes, triangles. Triangles, the building blocks of so many shapes, right? Coordinate geometry lets us find some very special points within these triangles. Points like the centroid, the incenter, the circumcenter, the orthocenter.
Whoa, that's a lot of centers.
There are a lot.
Are these like hidden control panels for the triangle?
In a way, yes. Each one of those points is defined by specific lines or properties within the triangle, and they each have these unique characteristics. So they're kind of like special landmarks, if you will, on our map.
Got it. And speaking of maps, illustration 4 seems to be guiding us towards one of these landmarks. What's the challenge here?
All right, so this one's a bit of a treasure hunt. We're given the centroid and 2 vertices of a triangle, and our task is to find the missing third vertex. So it's like we're using that centroid as our compass to kind of pinpoint that triangle's hidden corner.
I'm ready for the challenge.
Yeah.
But this illustration doesn't just stop at finding the vertex, does it?
You're right, it keeps going. By finding that missing vertex, we can then explore other special points that are associated with that triangle, like the circumcenter.
Okay.
So the circumcenter is the center of the circle that passes through all 3 vertices of the triangle.
Okay, so the circumcenter leads to the circumradius, which is like the circle's reach.
Yeah, exactly.
It's just amazing how one concept leads to another in this like geometric web we're weaving. Okay, so we've located points, measured distances, divided lines, and even uncovered these like hidden centers within triangles.
Right.
What's next on this coordinate geometry adventure?
Well, now that we're kind of getting a feel for these shapes, let's talk about their size. Specifically, how do we calculate the area of a triangle using coordinates?
Oh, good question. I remember formulas like using base and height and all that.
Yeah.
But how does that work with like the coordinates?
That's where coordinate geometry really shines. It provides this like really neat and efficient formula to calculate the area of a triangle using only the coordinates of its vertices.
So no more measuring bases and heights. We just plug in the coordinates. Boom, we get the area.
Pretty much, exactly. And this formula is especially useful when you're dealing with irregular triangles where those traditional methods can get really tricky.
Like a triangle shaped like a wonky slice of pizza.
Exactly.
Yeah.
To see this in action, let's look at illustration 6.
Okay.
It takes us through the steps of calculating the area of a triangle given its vertices.
Gotcha.
Demonstrating just how elegant and powerful this method can be.
This is incredible. I'm really starting to see how coordinate geometry can simplify these complex calculations. It's like having a super calculator for shapes. Okay, what other tricks does this system have up its sleeve?
Well, we touched upon collinearity a bit earlier, but it's worth kind of revisiting.
Yeah.
Remember, collinear points, they all lie on the same straight line. But what's really fascinating is that there are multiple ways to actually check for this using coordinate geometry.
We talked about the distance formula approach, right? What are some other ways?
Well, one really cool method involves actually calculating the area of the triangle formed by the 3 points.
Wait, so if they're all on the same line, wouldn't the triangle have 0 area?
That's it. You got it.
Okay.
And that's the key. If that area is 0, guess what? The points are collinear.
That's such a neat trick. So 0 area means a straight line. What if we do have an area? Does that always mean we have a triangle?
Well, if we're talking about 3 points, yes, it means we have a triangle. But what if we have a point that's constantly moving, tracing a path, according to some specific rules? That's where things get really interesting with this concept of a locus.
Ooh, a locus. That sounds like a mysterious place.
Think of it as the path a point takes as it journeys through the coordinate plane, following a set of instructions.
So it's like a mathematical treasure hunt. And the locus is the trail of clues left behind.
Yeah,
And I bet coordinate geometry helps us decipher those clues, right?
exactly. It gives us the tools to actually define that path mathematically, revealing that hidden pattern in that point's movement. Understanding loci is actually really crucial for problem solving in fields like physics and engineering.
Well, I can imagine. Like tracking the trajectory of a satellite
Exactly.
or designing the arc of a bridge. It's like we're uncovering the secrets of motion itself.
That's a great way to put it.
I love it. And to illustrate this, we have illustration 9.
Yes.
Okay, what kind of locus are we tracking in this illustration?
So this one shows us how to find the locus of a point that's dividing a rod as it moves along perpendicular lines.
Okay.
It sounds complicated, but with coordinate geometry, we can express this as a really simple equation.
So we're not just describing static shapes anymore. We're capturing motion and change.
Exactly.
This coordinate geometry is really starting to feel like a superpower. But wait, I see a whole bunch of equations ahead. Are we entering a new dimension?
We might be. We're about to dive into the world of straight lines
Okay.
and their many representations.
No, wait, aren't straight lines like pretty basic? You just draw a line. What's so complicated about that?
Well, you're right. Drawing a line is easy, but describing it mathematically,
Uh-huh.
understanding its properties, and then manipulating it for different purposes, that's where things get interesting. And that's why we have so many different forms of equations for straight lines. We have slope-intercept form, we have point-slope form, two-point form, intercept form, normal form. We even have parametric forms.
Whoa. That's a lot of forms for something that seems so simple. Do we really need all of those?
Well, each form has its own advantages,
Okay.
depending on what we know about the line and what we want to do with it.
Got it.
It's like having different tools in a toolbox, right?
Uh-huh.
You have a hammer, a screwdriver, a wrench. They're each designed for specific tasks.
Okay, I'm starting to see the value in having a versatile toolkit. And I see illustrations 12 and 14 are here to show us these tools in action.
Exactly. Illustration 12 gives us a scenario where we need to find the equation of a line knowing its intercepts, the points where it crosses the x and y axes,
Okay.
and another point it passes through. This is where the intercept form really shines.
Okay, so knowing those, like key points, helps us unlock the equation of the line.
Precisely. And then we have illustration 14, which throws us a bit of a curveball.
Oh, I love a good curveball. What's the challenge this time?
This time, we need to find the equation of a line based on the angle its perpendicular makes with the x-axis
Uh-huh.
and the area of the triangle it forms with the x.
Okay, that sounds way more complex than just knowing a few points.
It does, but this is where the normal form really comes to the rescue. It's specifically designed to handle these situations involving perpendiculars and distances.
So each form is kind of like a specialist
Got it.
for different line-related problems.
Exactly. And by understanding the strengths of each form, we can choose the right tool for the job and really unlock a deeper understanding of how these lines behave.
I'm really starting to appreciate the elegance and versatility of coordinate geometry,
Good.
but I'm feeling a little bit overwhelmed.
Take a breath.
Yeah. All this knowledge. Maybe we should take a break and then dive into the rest of these amazing concepts.
Sounds good to me.
Okay.
I'm just as eager as you to see what else awaits us in this realm.
All right, let's do that. Okay, so I think I've recovered from all that.
Good.
My brain is ready for more. We've explored points, lines, even like some special points within triangles.
Right.
So what's next on this mathematical treasure map?
Well, remember all those different forms of equations for straight lines? Those
Yeah.
weren't just for show. They actually they lay the groundwork for understanding some really cool relationships between lines.
Okay, so we're going beyond just describing like individual lines now.
Exactly.
We're starting to see how they like interact with each other.
Exactly. Think about parallel lines, for example.
Okay.
They run side by side, they never intersect. In coordinate geometry, we can actually instantly recognize parallel lines just by looking at their slopes.
Wait, slopes? Isn't that like how steep a line is?
Yeah, that's right. It's a measure of how much the line rises or falls as we move along that x-axis.
Okay.
And here's the key. Parallel lines have the same slope.
So it's like they're climbing the same hill at the same angle.
Yeah, exactly.
Okay, that makes sense. But what about perpendicular lines?
Right.
Those are the ones that intersect at a right angle, right? What's the secret to their slopes?
Perpendicular lines are a bit more dramatic. Their slopes are negative reciprocals of each other.
Negative reciprocals. Okay, that sounds a little complicated.
It's actually simpler than it sounds. So if one line has a slope of, say, 2,
Okay.
its perpendicular pal will have a slope of -1/2.
Okay.
So you just flip the fraction and you change the sign.
Okay, I'm seeing a pattern here.
Mm.
So just by like glancing at the slopes,
Yeah.
we can tell instantly if lines are parallel, perpendicular, or just doing their own thing.
Exactly. And this really simple relationship between slopes actually unlocks, the deeper understanding of angles and intersections in geometry.
Now, when we talk about parallel lines, I can't help but think about the distance between them.
Right.
Is there a way to like measure that using coordinate geometry?
Absolutely. There's a formula specifically designed to calculate the distance between parallel lines.
Okay.
And this isn't just some theoretical concept. This actually has practical applications in fields like architecture and urban planning.
So when architects are designing buildings,
Yeah.
or city planners are laying out streets,
Mm-hmm.
they're secretly using coordinate geometry.
All the time. You bet. Think about the width of a road, for example, or the spacing between railway tracks. These calculations rely on understanding the distance between parallel lines.
Wow. So coordinate geometry is like the hidden framework of our built environment.
It is.
That's pretty cool. But let's zoom back in on those lines. Is there a way to tell if 2 points are like on the same side or opposite sides of a line?
That's a great question, and that actually leads us to a really interesting connection between coordinate geometry and inequalities.
Okay.
It's not just about where the points are, like visually. We can actually use their coordinates and the equation of the line to figure this out.
So the coordinates like holds clues about which side of the line a point is on.
Exactly. If you plug those coordinates into the line's equation, the signs that we get, positive or negative, tell us the location of that point
Interesting.
relative to the line. It's like the line is dividing the plane into 2 teams, and the coordinates reveal which team that point is playing for.
Okay, I'm starting to see how coordinate geometry can answer some pretty sophisticated questions.
Yeah.
What other relationships between points and lines can we explore?
Well, sometimes lines don't just intersect casually. They have a very specific meeting point. We call this concurrency. And this is where 3 or more lines intersect at a single point.
Oh. So it's like a grand intersection where multiple paths converge.
Exactly. And coordinate geometry gives us the tools to determine if lines are actually concurrent. We can use something called determinants, which are these, special calculations involving the coefficients of the line's equations.
So it's like using a mathematical formula to see if those lines are like destined to meet at a specific point.
Exactly. And this concept of concurrency actually has applications in various fields. For example, in physics, the 3 medians of a triangle, those are the lines drawn from each vertex. The midpoint of the opposite side are always concurrent. They meet at a point called the centroid, and that represents the triangle's center of mass.
Oh, interesting. I'm noticing this recurring theme here. It's like coordinate geometry connects like these seemingly abstract concepts to real-world phenomena.
Yeah, absolutely.
Amazing.
Yeah.
Okay, what other geometric wonders can we explore with this system? I see something about reflection.
Ah, yes, reflections. These are all about symmetry. Imagine looking at yourself in a mirror.
Right.
Your reflection has the same shape, but it's flipped across that mirror's surface.
Right. And I bet coordinate geometry gives us a way to capture this like mirroring effect mathematically.
You bet. We can actually use formulas to calculate the coordinates of a point's reflection across various axes and lines.
Oh, wow. So it's like we're using equations to create mirror images.
Exactly. And these reflection formulas aren't just for fun. They actually have applications in fields like computer graphics, optics.
Oh, I can imagine creating realistic reflections in video games or, designing lenses that bend light in specific ways. It's like coordinate geometry is the secret language of visual effects.
It is. And to illustrate the power of these reflection formulas, we have a rather elegant example in our sources.
Okay, what's being reflected in this case?
Well, it's not just a single point. It's an entire line being reflected across another line.
Whoa, reflecting a whole line. Okay, that sounds pretty complex.
It is, but the beauty of it is that coordinate geometry actually provides a way to represent this transformation using a relatively simple formula.
So we can capture the essence of this like mirrored line using just a few symbols and numbers.
Exactly. It's a testament to how concise and powerful mathematical language can be.
It's like I'm learning a secret code for for unlocking the universe's like geometric mysteries.
I like that.
I love it. Okay, so we've reflected points and lines. What other transformations can we perform with coordinate geometry? I see something here about shifting the origin. Is that like moving our home base on the map?
That's a great analogy. Shifting the origin and rotating the axis are transformations that allow us to view geometric shapes from different perspectives
Sure.
without actually changing the shape itself.
So it's like we're adjusting our camera angle
Yeah.
to get a better view of the landscape.
Exactly. Sometimes, by shifting our perspective, we can actually simplify equations or reveal hidden symmetries that weren't apparent before.
It's like we're putting on a special pair of glasses
I like it.
that reveal like the hidden structure of geometric shapes. And I see illustration 28 is here to demonstrate this concept.
Yes, this illustration shows how rotating the axis by a specific angle can actually transform a complicated equation
That's
into
nice.
a much simpler form, making it, much easier to analyze and understand.
It's like we're rotating the problem itself to find a more elegant solution.
Exactly. Exactly. And this technique is particularly useful in fields like physics and engineering, where understanding a system's symmetry can really simplify calculations and lead to, deeper insights.
Incredible. I'm starting to see how coordinate geometry is not just about like plotting points and drawing lines.
Yeah.
It's this powerful framework for analyzing shapes, understanding their properties, and just solving this wide range of geometric problems.
Absolutely. We're not done yet. There's still more to explore. Let's move on to another intriguing concept, angle bisectors.
Okay, angle bisectors. They sound familiar, but I'm a little fuzzy on the details.
Sure.
What exactly are they?
Okay, imagine you have two intersecting lines, right,
Yeah.
forming an angle. An angle bisector is a line that neatly divides that angle into two equal parts.
Got it. So it's like a perfect splitter for angles.
Exactly. And it's important to remember that there are actually two angle bisectors for any pair of intersecting lines, one for the acute angle and one for the obtuse angle.
Ah, okay. So we have a choice of which angle to bisect.
We do. And depending on the problem, we might need to find one or both of these bisectors.
Gotcha. And I see we have an illustration to kind of guide us through this concept. Illustration, come on. What's the scenario here?
So this illustration shows us how we can find the equations for both angle bisectors of a
Alright.
given pair of lines. It also shows how to determine which bisector corresponds to the acute angle and which one corresponds to the obtuse angle.
So it's like we're not just bisecting angles, we're also labeling them.
Exactly. And understanding this distinction between acute and obtuse angle bisectors is important for solving various geometric problems.
Okay. I'm ready to bisect some angles.
Good.
But before we get too carried away, I see another concept looming on the horizon. Families of lines. It sounds almost like a social gathering for geometric objects.
Well, in a way it is. A family of lines is a set of lines that share a common property.
So it's like a club for lines with like exclusive membership criteria.
Kind of. For example, all the lines passing through a specific point form a family,
Okay.
or all the lines with a certain slope form another family.
Got it. So it's like grouping lines based on their like shared characteristics.
Mhm.
But how do we represent these families like mathematically?
Well, that's where parameters come in. We can use equations with parameters to describe an infinite number of lines
Okay.
with a single equation.
So it's like a super efficient way to represent a whole bunch of lines at once?
Exactly. And this concept of families of lines is incredibly useful in geometry and other fields like, physics and engineering.
I can imagine. Instead of dealing with individual lines, we can like analyze and manipulate like entire groups of lines simultaneously.
Yes.
It's like we're conducting a geometric orchestra.
I love that analogy.
And to demonstrate the power of this concept, we have illustration 31.
Yes.
Okay, what family drama is unfolding in this illustration?
So this one shows us how to prove that an entire family of lines passes through a fixed point.
So even though these lines might like seem to be going in different directions, they all have this common meeting point.
Precisely. And we can prove this very elegantly using this concept of parameters and algebraic manipulation.
It's amazing how a seemingly like abstract algebraic technique can reveal like hidden geometric relationships.
Yeah.
I'm really starting to see how coordinate geometry is like this bridge between the visual and the symbolic.
Exactly. And that's one of its, greatest strengths, right? It allows us to translate geometric ideas into algebraic expressions and vice versa. And it enriches our understanding of both worlds.
All right, so we've explored families of lines. What other fascinating geometric creatures await us in this coordinate jungle?
Well, we've talked about single lines, we've talked about groups of lines.
Right.
But what if we have a situation where a single equation represents not one, but two straight lines?
Whoa. Two lines in one equation. That sounds like a mathematical magic trick.
It's more common than you might think. We call this a pair of straight lines, and there's a specific condition involving the coefficients of that equation that tells us if it represents such a pair.
So it's like the equation is like hiding a secret twin line.
You could say that. And if that condition is met, we can then delve deeper, find the equations for those individual lines, the angle between them, and even determine if they're parallel, perpendicular, or coincident.
Coincident. What does that mean?
That means the two lines are actually the same line. They overlap perfectly.
Oh, so it's like the equation is playing a bit of a disguise game.
It is. It is. And to see this concept in action, let's look at illustration 32.
Okay, what kind of line pair puzzle are we solving in this illustration?
So this illustration uses the condition for a pair of straight lines to find the value of a parameter that would make a given equation
Okay.
represent two lines instead of just one.
So we're manipulating the equation to like reveal its hidden twin.
Exactly. And by analyzing those coefficients further, we could even determine if those lines intersect, are parallel, or perhaps even coincident.
Fascinating. I'm starting to see how even like seemingly simple equations can hold this wealth of geometric information.
Yeah, absolutely.
What other secrets can we unlock using coordinate geometry?
Yeah.
I see something here about lines joining intersection points to the origin.
Ah, yes, this is a clever technique that combines the power of lines and curves. So imagine you have a line intersecting a curve at 2 points. This technique allows us to find the equations of the lines that connect those intersection points back to the origin.
Oh, so we're drawing lines from the very center of our coordinate system to those like special meeting points between the line and the curve.
Exactly. And we can do this by using a concept called making an equation homogeneous.
Homogeneous. That sounds intriguing. What does that mean?
It's a way of rewriting an equation so that all the terms have the same degree. And by strategically substituting the equation of the line into the equation of the curve, we can transform that equation into a homogeneous form.
Okay.
And that allows us to derive the equations of those lines joining the origin to the intersection points.
So it's like we're using a special algebraic maneuver to reveal those hidden connecting lines.
Exactly, exactly. And to see this technique in action, we have illustration 35.
Okay, what's the geometric puzzle in this illustration?
It involves finding a specific value of a parameter that would make a chord of a curve subtend right angle at the origin.
A chord subtending a right angle.
Okay, that sounds pretty specific.
It is, but this illustration really elegantly demonstrates how we can translate this geometric condition into an algebraic problem and solve it using this technique of making an equation homogeneous. It's a beautiful example of the interplay between algebra and geometry.
This whole deep dive has been a revelation. I'm starting to see coordinate geometry not just as like a set of formulas and procedures, but as this powerful lens for understanding shapes, their properties, and how they interact with each other.
I couldn't agree more. It's like we've been given this new language to describe and analyze the world around us.
And it's a language that opens up so many possibilities. We've seen how coordinate geometry is used in architecture, engineering, physics, computer graphics, even optics. It's truly a universal tool.
Absolutely. And what's even more exciting is that we've only just scratched the surface. There are countless other applications and extensions of coordinate geometry waiting to be explored.
But for now, I think it's time for us to wrap up this deep dive.
I agree. My brain is feeling pleasantly full of geometric goodness.
Yeah.
But before we go, I bet you have a final thought-provoking question to leave our listeners pondering.
I do. We've seen how the section formula can divide a line segment into a specific ratio. But what if we wanted to divide an area or even a volume into specific ratios using coordinates?
Oh.
How would we approach that challenge?
Ooh, that's a good one. It really takes the concepts we've explored today
Right.
and pushes them into a whole new dimension.
Right.
I'm already starting to brainstorm ideas.
That's what we like to hear. That's what we hope for with every deep dive, right? To spark that curiosity, to ignite new ideas, and to equip you with the tools to explore this fascinating world of mathematics.
Well, it's been a true pleasure navigating this geometric landscape with you.
Likewise.
And to our listener, thank you for joining us on this deep dive into the world of coordinate geometry.
Keep exploring, keep questioning, and keep that mathematical spark alive. Until next time.